Okay, let's get started. So we're going to start reviewing logistic regression and gradient ascent or gradient descent, depending on the sign. And then we're going to talk about neural networks. So logistic regression, which we talked about last time, is a probabilistic generalization of the perceptron algorithm that we spoke about a few classes ago. And we have some weight vector, W, which will change our the probability distribution assigned by a model. And what we are going to use to pick this weight vector W is a data set. So we'll have each of these i's represents an example. We'll have an example X, an example Y, many more examples X, many more examples Y. And we're interested in finding a W which affects the probability distribution in such a way that when fed in an X example, it puts high probability on the actual Y example that was actually observed. So we want the model to retrodict, that would be the term here, the data. We want it to, and retrodict means basically to predict, but you're kind of re-predicting something that you already know the outcome of. So we want a model that would have predicted correctly if it hadn't, if we didn't know what this was going to be. So this probability distribution will assign probabilities to all the possible different Y's. But then what we're most interested in for scoring our W is how much probability did it assign to the actual Y that was actually observed. And the higher the probability, the better we say it did. And if you assign, let's see, if you assign 50% probability to the truth here and 50% probability to the truth there, that's about as good as having assigned 1 in 4 probability to the truth here and 100% to the probability of the truth there. Because in both cases, you've assigned 1 in 4 probability to the whole set of what you saw. And so what you want to do with probabilities is multiply them. But for convenience, it's easier to just take the log and then add them. And so then this is the log likelihood assigned to the whole data set given the W. And we want to maximize, we want to pick the W that maximizes that expression. Now for logistic regression in particular, well, backing up a second, this basic form will look the same for neural networks when we get to it, but the definition of P and the way it depends on W will change. So for logistic regression, here is the way that P depends on W. We featureize our input, we turn it into a vector, we take the dot product with that W, and then the amount of, and then this expression is equal to the probability assigned to Y being +1, and this is the probability for the other situation. So in this, in logistic regression, the convention, I guess, is that the labels yi either take the value of +1 or -1. So this would be binary classification for logistic regression. Yeah?
So are the x's and the w, are those the evidence variables?
Evidence variables. Have we used the term? Oh, are you using the term evidence variable in a similar way to like hidden Markov models?
Sort of,
Yeah. Yeah, that's a pretty close analogy, I'd say. I mean, it's like a bit of a disanalogy is often in machine learning. These examples will be connected from something that is totally causally independent for a prediction we're making, but they come from the same world, and so they tell you something about properties of the world. And so, yeah, you can think of this whole data set as evidence variables about how other y's will depend on other x's. But yeah, this is basically we're trying to learn a connection between these x's and these y's based on lots of examples of x's and y's. And in this setting, the y's happen to take this very simple form where it can either be positive or negative classes, and the x's can take these more elaborate forms where it's any, the relevant features form any vector in what could be a big vector space. Okay, any other questions about binary classification using logistic regression, besides the question of how we find this, which we'll get to later. This is the problem statement. This is what we're trying to do when we're picking a W. Okay. Multi-class logistic regression. Same idea, really, but it just gets a little more complicated with all the symbols we're dealing with. So this is the same as before. But now the dependence of P on W looks a little different. So like I was saying before, with neural networks, the dependence of P on W will look different still. But here it is. For a multi-class logistic regression, it's not too dissimilar. So let's say what we need now is not just one W vector, basically pointing toward the positive class, which is all we needed in binary classification. We need a vector pointing to each of the classes. So this is a 3-class logistic regression. You could have many more, and then you'd need a vector for each of them, a vector W. And what we do to compute this probability is first we come up with a feature vector for the data point in question. So here I've drawn it like this. And then we look at the W vector associated with the actual class that this xi belonged to. So let's say, for instance, that this xi belonged to class number 3. So then this would be W3. So then we'd look at the dot product of this and that. Okay, maybe it's a little positive, but not very big. And then we'd divide and we'd exponentiate it. And then we'd divide it by the sum of what we would have gotten if we'd, if it had been in any other classes. So in the denominator here, we take this dot product, exponentiate it, take this dot product, exponentiate it, take that dot product, exponentiate it, sum it all together. That's our denominator. And the numerator is just the true class. And that's how we compute the probability that it assigned to what was actually observed. It being multi-class logistic regression model based on this W. So if our multi-class logistic regressor is using this W, this is the probability that it assigns to the actual Y given the actual X. And so we'll plug that in up here. We'll want to maximize the sum of the logs of that over our whole data set. Yeah?
Why do we exponentiate the dot product?
Because we want it to be positive. And dot products can be positive or negative. We basically need to get 3 arbitrary numbers and turn them into positive numbers that sum to 1. So we exponentiate them to make it positive, and then we divide by their sum to make them sum to 1. There's also kind of an analogy to thermodynamics that people use sometimes that makes this form make a little more sense. There was the form of the sigmoid function that I was loosely justifying last time with, kind of mounting evidence for something between hypotheses, but I think the answer that a lot of practitioners would give is it makes it positive. Okay, any other questions? Okay. So what's still needed, as I just alluded to, and which we began to talk about at the end of last time, how do we find this W that maximizes this pretty elaborate expression? Okay, so now we're on to optimization in neural nets. We reviewed this last time, not going to review it again. Here is the gradient. That is the vector of partial derivatives with respect to all of the given variables. So we have this function g, which is a function of 2 variables. So then the gradient is a 2-dimensional vector of each of the partial derivatives. And the approach, which I talked about at the end of last class, is hill climbing. We start with some random W vector, and then we improve it. And we keep doing that until it looks like no small changes would lead to any improvement. this is optimization over continuous space. So rather than like looking at all of the close alternatives, we can compute the gradient, and that will tell us among among all the options in a ring around you or in a hypersphere around you, you can just compute analytically which is going to be the best. Okay, in 1D optimization, there's not so much value added by gradient because it's only kind of 2 alternatives to try. But in more dimensions, if you think about all the different possible directions you could go, there are a lot to try. You could still try to discretize it, but it would end up being a lot anyway. And so it's better to just compute, okay, that's going to be the direction that increases my likelihood the most. So if we go back to this expression, if we have a given W, so now we're not maximizing it anymore, we're just thinking about what is the log likelihood of a given W, we can compute, and so W is a big vector, we can compute exactly which direction to change W that will most increase this log likelihood, which is an incredibly powerful tool. Because if you have like a vector of 200, and you think, okay, well, I could increase this one, I could decrease that one, I could increase this one, I could decrease that one, go through all of them, that's 2n different possibilities, and in fact, it's hard to visualize high-dimensional space, but that would be an extremely impoverished view about all your neighbors because so many of your neighbors involve increasing and decreasing multiple at the same time. And if you were looking at like, increase, 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 decrease, 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 and you're thinking about all those possibilities, that's now 2 to the n different possibilities, totally hopeless. Much better to just compute what's the most promising direction. Okay, so then we get to gradient ascent, or gradient descent if the thing you're thinking about is something you want to minimize. And that takes this form. So we have our weight vector. This is just a 2-dimensional weight vector, but if we had more dimensions, this would be comma W3, comma W4, and so on. And this would be, W1, W2, it would go on down that way as well. So for each of these single weights in our potentially big weight vector, we compute the partial derivative of the function we're interested in maximizing or minimizing. So in this case, we'd have the log likelihood function of W here. We compute the partial derivative of that with respect to this given weight. And then we move in that direction. This alpha is going to be some number that will dictate how how much we're kind of chomping at the bit to go in that direction. If alpha is really high, then we note that if I go a tiny bit in this direction, it's definitely going to be improvement. I might as well go way in that direction, because if I only go a tiny bit, I'm not making much progress. But the gradient is really just saying, all the gradient can say for sure is if you go a tiny bit in that direction, that's going to be a good improvement. It doesn't tell you anything about it might all of a sudden you move and now the situation's totally different. So you can run into problems if you have a higher alpha, which I'll describe later. Yeah? Infinitely small, and you're guaranteed to improve G. And as you make it bigger, it's not guaranteed anymore, but if you were only doing infinitely small every step, you'd never get anywhere. So you kind of have to, there are more clever things you can do, but that's the fundamental trade-off. Okay. Rather than writing comma W3, comma W4, comma W5, and then writing the update rule for each one of those in turn, it's easier to write in this notation where you have this is a vector, that's a number, this is a vector. So that's just saying it's just a list of all the partial derivatives of all the components of W. There you go. That's what it is. Okay, we didn't, right, it's called the gradient. We didn't really have time last class for questions really at this point, so any questions about this update rule. Yeah.
What is the difference between using a smaller alpha and a larger alpha?
I have a picture coming up that I think will help with that discussion, but I'll be sure to get back to it. The question was the difference between using a smaller alpha and a larger alpha. Too small and it goes too slow, too large, and I'll show you what happens. Okay. Okay, and so here's a picture with a fairly small alpha, maybe. These are contour lines, so this is right now, this is the highest contour line, and these are slightly lower, so this is kind of a hill coming out like that. We start here, so this is our two-dimensional weight vector, and we see that the partial derivative in this direction is pretty big, well, pretty negative, I guess. Partial derivative in this direction is a bit negative. So that's kind of how fast this level is increasing if we go that way, how fast this level is increasing if we go that way. This is a bigger number, so you can see the direction is more leaning down than leaning left. And so this is the direction we go in. And it's pretty, I mean, in absolute terms, the gradient is pretty big, so we take a pretty big step. And now you can see, I mean, you can't really see the contour lines, but you can imagine that it's kind of leveling off. And so the gradient is smaller in magnitude, so our step's going to be smaller, and it's also kind of started turning a little in this way. And we keep doing this. Now we get to here. The steepest direction is really mostly that way, and so we keep going until we get to the top. And if you increase the learning rate a bit, I bet you'd get there in fewer steps. Okay, there's the gradient in n dimensions. And our optimization procedure is this. Like, so simple, really. You just start somewhere and you make a series of improvements until you don't want to anymore. And then you stop. Okay. Yeah, we've discussed a little bit the issue of coming up with a good alpha. And I guess a rule of thumb, which I hadn't actually heard before, but is that you kind of want alpha to change a little bit, but not too much. Okay, so now we're still kind of avoiding the question about computing all of these derivatives. And we're going to talk about neural networks first, which are a generalization of logistic regression, and then talk about some tools for computing these derivatives. I mean, in theory, like, you can just do it. It's just a pain. But there are ways to do it with software that are not even a pain. Okay. So deep learning has done some pretty impressive things recently. So let's talk about what it is doing. We're only going to really talk about it at a pretty high level, but honestly, a lot of the more intricate stuff is just people have been trying things out and seeing what works. So there's a whole host of things to discuss about that, but we don't have time to get to them in this class. So when Cam was first talking to you about perceptrons, he mentioned that first we have to turn our data point into some vector of numbers. And then once we have that, we can do machine learning to figure out how the class that we're trying to learn depends on this vector. But how do we get this feature vector? And in deep learning, the idea is kind of to learn these features rather than just have them fixed. So to review the perceptron, we have features of x, x1, x2, x3. We have weights, w1, w2, w3. Obviously, there could be more. We multiply the x's with the w's. We add them together. We check if it's positive. And that determines the class that the perceptron outputs. Now with logistic regression, instead of just outputting positive if it's positive, negative if it's negative. We output a probability that it's positive according to the sigmoid function applied to this output. So that's 1 over 1 plus e to the negative that dot product. And in a neural network, in a neural network with sigmoid activations, we are basically combining logistic regression pieces end to end. And in fact, you can use other activations, but the initial activations that people tried were sigmoid activations, probably because of their connection to logistic regression. So here is a neural network. It has 2 layers, 1, 2. It has 2 neurons, 1, 2, and it has lots of W's. But at the end, we're still going to go back and say the log likelihood is the sum of the log over the sum over all the data points of the log of the probability assigned to the correct output given the data point and given all these W's. And then we're going to try and tune all these W's to maximize that quantity. So, you end up having to do annoying things with indexing, like these are, you have 2 subscripts here. If you were, comparing these 2 layers, you might put some superscripts in to tell you which layers. But, of course, oh, we're missing an arrow, aren't we? There should be an arrow there. Is that? Oh, yeah, there is. Sorry, there it is. Sorry. Okay, so you have all these numbers, and you just learn them all at once with gradient descent. So this you can think of what's going on here as intermediate outputs. So let's call this intermediate output H1, and this will be H2. And so this takes this form. This is the sigmoid function, so we don't have to keep writing it out like this: 1 over 1 plus e plus 1 over 1 plus e to the negative thing. We just write phi of that thing. So H2 takes this form. H1 took that form, and then y takes this form. So the easiest way to write it out in math is by naming these outputs, defining them, and then defining this in terms of these intermediate outputs. Otherwise, the whole expression would just balloon outward in complexity. So we're basically treating these as if they're the new inputs to our problem. So this is kind of like we're doing logistic regression based on these features, and these features are learned from more basic features. Any questions about the computation that's being depicted? Uh-huh.
Can you clarify how you get H1?
Yep. H1, so first we look at all of the weights that are going from each of these inputs to this top one. So this is H1's home up on the top. So we take the dot product of our x vector with this this kind of vector. So you can think of this as 2 vectors. You could stack them on top of each other in your head if you like. But this is kind of one vector, this is kind of another vector. And now this is going to be the dot product of this and that. And then you run that through this sigmoid function. So it's the sigmoid of the dot product of this and that. Or if you prefer to think in scalars, the sigmoid of this times this plus this times this plus this times that. Yeah. That's just the definition. This sigmoid function phi of something means 1 over 1 plus e to the negative that thing. Yep. Are thicker. The idea is that these, I think it would be hard in this scheme to depict negative weights, which you can have, but I think what they're aiming to depict here, Peyron made these slides last semester, is like this is a bigger weight. So it's like this number is kind of a mixture of these three numbers, but it's more dominated by these two. Yeah. Yep.
Why is it 2 neuron and not 3? Is the one in the last layer not?
That's right. Yeah. Obviously, well, I'll show you ones with more layers, and then there's not, I mean, there could be different numbers in each of the layers, although often people will have, for most of the layers, they'll have the same number of neurons. But yeah, this is just saying per hidden layer. Yep. Sorry, what was that? Like where the sigma function comes from, like why it takes this form. You could look back at the slide that I showed you last time, which kind of motivated where it comes from, but it ends up not being so important. I mean, this activation function has kind of fallen out of fashion for neural networks anyway, so you can use other activation functions. It's just kind of this is the old classic. Yep.
Once one of the neurons are activated, what goes on in the second layer?
So by activated, I guess you just mean like once we've figured out what value it takes. Yeah. So these will take some value computed by this process, and then we use these values as if there are new x's for going into the next. So we have some new value here, which we call h1, and then h1 times w1 goes into this. h2 times w2 also does. We add them together. So here, that's what we do with them. So our h1 and h2 are the activations of these intermediate neurons, and this is what we do with them. We use that as our new vector. We take the dot product with this w vector, or alternatively, take the product and sum them, and then we pass it through a sigmoid function again.
But
Yeah.
in this particular case, would it be kind of arbitrary because each result would output the same result in the end? Why?
Sorry, can you?
Yeah, as in the second layer, there's only one neuron that we have,
Yeah.
and that results in y. So, and just in this case, I'm just asking if it's arbitrary, as in no matter which neuron we choose, which activates in the first layer, it'll just result in the same neuron in the second layer.
So it's not an either or which activates. So activation is not a binary thing. These will take, well, the sigmoid function outputs something between 0 and 1. So if we're using a sigmoid activation, these will all have outputs that are either 0 or 1. Depending on what those outputs are, they would change the value. If we kind of flipped the position, then it would if we flipped this for that, this for that, this for that, and this for that, those 4 pairs of weights, the neural network would have exactly the same behavior. I don't know if that's what you were getting at or if that's a separate point.
That makes sense.
But yeah, the hidden the values of h1 and h2 absolutely will affect the y's. Yeah, if this one increases, then and if w1 is positive, then this will increase and that will increase. Same down there. Okay. Yeah.
Is it generally the case that each layer removes one variable? Like one
No.
No.
Yeah. How do you calculate the number of W's? You pick at the beginning how big a network you want to train. So, you know, I'll show you some more examples later of like bigger networks that are either deeper or wider. Yeah, so you're starting with a W vector and then you're trying to improve it. You can pick whatever kind of shape and size you like. And there's a whole industry in trying to come up with good ways to do it. Other questions? Okay. So here it is written all out. If you didn't label intermediate computation steps as H1 and H2, you'd have to write it like this, which is just harder to read. Okay, or if you really want, you could write it like that. Oops, sorry. Hello, okay. So here it is how we've written it before. The output is this sigmoid of the dot product of the weights with the hidden layer, and the hidden layer is defined, each of these H quantities are defined like that. We could also write it this way. So this vector, h1, h2, can be written as this vector, the input vector, x1, x2, x3, multiplied by this matrix. So this is going to be, so we have 1 by 3 and 3 by 2. So our output is going to be 1 by 2. Okay, that's good. That's what we want. The first and only row, first column, is going to be first and only row, first column. Okay, so that's good. That's the dot product we want. First and only row, second column, first and only row, second column. That's the dot product we want. And so this picture, this matrix definition is, it's giving us the thing we wrote out up here. Great. And it's a nice shorter way of writing it. So we can write our H vector defined in this way. And that's just following the rules of matrix multiplication. And it allows you to write it a little shorter. And then your Y is just going to be the dot product of this vector of hidden layer values, times our new weight vector for the next layer. And then you take the sigmoid of all that. And so then, when you write it out like this, you can write it much more compactly. Now we have our input vector. We have a matrix of weights. Our hidden vector is the sigmoid of this matrix product. And then our output is the sigmoid of this matrix product. And if you don't like all the subscripts and superscripts, then you'll prefer this. If you don't like matrices, then you'll prefer that. Any questions about matrix multiplication and how we've allegedly simplified the expression? Okay. If you don't like either matrices or all those symbols, I'm sorry. Okay. So this is our same two-layer, two-neuron neural network that I showed you before, and this is the shapes that I was kind of talking through. So here is our input feature vector, which was drawn as a row vector, so 1 row, 3 columns. This was the matrix, which was 3 rows, 2 columns, and so that gives an output of 1, 2. Similar thing going on here. The shapes I'll check out when you're coding in PyTorch or whatever you're using. There's just lots of issues from things having the wrong shape. Should it be 3, 2? Should it be 2, 3? You just try it both ways and see what works. Okay. Same idea, but now we have a third one, just to show you that, you could set up a model like this if you prefer. This is going to be more expressive, but there's more weights to learn, and so maybe you could overfit to the data. So again, we have kind of a line going from everything in this layer, our input layer, to everything in this hidden layer. So this is going to be 3 vectors, you could think of them as. And now we have this over here, really the same thing. And so now our hidden layer, we'll call them H1, H2, H3, and it will be defined like this, the sigmoid function applied to this matrix product. And so again, you can see H1, that's the first row, first column. So we go first row, first column, we have x1 times w11, x2 times w21, x3 times w31. We can see that that is exactly what we were hoping for from this picture to get to this dot product up here. And so you can see that when you write things out this way, h1, which is the value here, is defined correctly. This, you know, the rules of matrix multiplication have given us what we want. So this is defined in this way. We've just added another row to this. And now we've added another row here, another column there. It's basically the same, but any questions? Yeah. Yes, that might even be coming next. Yes, we could. Okay. Yeah, same thing as before, but some 2s have changed to 3s. The shapes check out exactly as they did before. Okay. It's not quite coming next. It's coming soon, though. Unsurprisingly, you don't need to stop at 3. You could go all the way to n. And now you'll see that this matrix could be getting pretty big. It will have, so this weight matrix in layer 1, it'll still have 3 rows. Yep. But now it will have n columns. And so then this hidden layer will have n columns as well. So there will be n different hidden values, and that'll all be fed into the final layer. Okay. Yeah. No, please. Sorry. We know 2 of which we can compute. Right, x. We have x and y, and we're trying to compute w. Is that right? Yeah, so you're kind of saying if we have x and w, could we predict y? If we have y and w, we could predict x. Is that kind of your question? So when we use the neural network, it is in fact the case that we have x and w, and we're trying to predict y. So that definitively answers that question. When we're training it, we have examples of x's and y's, and we're trying to come up with a good w. When we actually use it for new w's, if we want to come up with the class, then we take the w's, we take the x's, we feed it through, we come up with new y's, and those are our predictions. And yeah, there are cases where you have the y's and you have the w's, and you're trying to come up with they end up not looking so good, at least with neural networks, come up with x's that would like with image classification, some people were like, oh, what's the most dog-like image? And so they tried to come up with an x that would, given their weights that they'd learn, produce like a really certain output that, oh yeah, this is definitely a dog. And it ends up with an image that looks nothing like a dog. Yeah. Yes. The most tricky bit is getting from x's and y's to determining the w's. And to do that, we do gradient descent on our log likelihood function, trying to find a sequence of w's that are better and better and better at assigning high probabilities to the true y's when the true x's are input. Yeah.
Are the weights in layer 1 different than layer 2?
Yeah. Yeah, to repeat that, the weights in layer 1 are different than in layer 2 in general. Okay. I think this is the same thing I showed. Oh, yeah. There could also be as many input dimensions as you like. So this doesn't have to be 3, obviously. It could be as many as you like. Yeah?
When in this scheme would we actually perform gradient descent on our log likelihood functions to find our probabilities?
That's, yeah, we'll get to it in a second. I mean, it's kind of like, describing the loss function basically, and then I'll describe like how we come up with, yeah, basically right now this is depicting the dependence of the probability outputs on W, how the different W's will affect the output. And that's obviously the first step to figuring out how do you optimize that. But yeah, haven't quite gotten to that, getting to it soon. Kind of. I mean, the answer is basically just going to be we have a program do it. Yeah. Okay. So if we have more input features, then that's how these shapes would change. The shape of the input would, you know, it would be a longer row vector, so more columns, there'd be more rows there. So what I was depicting before, there's just one output, and so that's kind of like the binary classification setting or a regression setting where you're just trying to produce a single number as output. But if you had multi-class regression, multi-class classification, or if you're trying to do regression predicting multiple scalar targets, then you might have multiple outputs. Still works basically the same way. So this is all to say that this is a pretty general category of ways of converting a vector of parameters into a prediction about, a probability distribution over outputs given inputs. Okay, so there's a more general form where this number, it's not a number here, this is just the dimension of x. And then this shape is dimension of x, and this is n, the number of neurons in the hidden layer. So that could be anything you like. And then, here's the shape of the hidden layer vector. Now it's length n. Here's the shape of the second weight matrix, n by the output dimension. And so this is the most general form that all these shapes can take. Okay. Let's add a layer. So this was your question recently. Can we add layers? Yes, we can. This is 3 neurons per hidden layer. This is 3 layers or 2 hidden layers, 3 layers of weights, 2 hidden layers. And okay, how many, here's a little question for you. How many parameters are in this? How many W's, how many different scalar values of W are in this whole network? Yeah. It would be, I should have been thinking about this myself after I asked it. Yes, it would be 21. These arrows don't count. This is just saying the dot product goes into the sigmoid function, but all these other arrows do count. So we have 9 here, 3 by 3, 9 here, also 3 by 3, and then 3 there. So 21. Okay. Here are all the shapes. I think I'll just let you review this on your own time if you like. The shapes work out. For the weight vector, the number of rows is going to be equal to the number of neurons on the left. The number of columns is going to be equal to the number of neurons on the right. I'm 90% sure I said that right. Well, it's 3, 3 in this case, so it doesn't matter. Yeah, that'll make all the products work correctly. And then the input and output layers plus all the hidden layers, they'll be vectors. They'll be row vectors. Okay. So there's all the shapes they'll take. Yep, I got that right. The number of rows is equal to how many neurons are on the left of it. The number of columns is how many neurons are on the right of it. Yep, sorry. Questions? Yeah.
Does every age generally have like a well-defined known feature it's describing? Or is it
No, not remotely. The question was, does every H describe some like intuitive known feature? Not at all. There are a lot of people working on trying to figure out what is going on with these internal activations. Sometimes what they can do is they have some concept that they think must be represented somewhere because it seems to understand it. And so then they try and figure out which neurons have higher values when it must be thinking about this concept. And so what they can sometimes say is like, okay, if you take all of your neuron activations and put them in a vector, the more that it's pointing in that direction, the more it's thinking about this concept. That's kind of what, that's called a linear probe, I think, for figuring out like how it's representing a concept. But often it will be spread out over many different neurons. And I think people have probably come up with better tools besides linear probes for thinking about how a network is representing a concept, but in any case, it's very rarely in one neuron. And a single neuron can often have like multiple duties in really big neural networks. Like the neuron is like unusually active when it's thinking about France and when it's thinking about running or whatever. Yeah. Other questions? Okay. So, multi-layer neural network. The input to a layer will be some input vector. The output will be some output vector. To get from the first to the second, we multiply the vector by some matrix of weights, and now we get a new vector that has the right length. Then we apply some nonlinear function, like the sigmoid function, to modify our output. Nonlinear function is any function that's not a line, is what I mean by that. So the big idea here is we can chain layers together. They can basically be doing computation, serial computation, that is useful for understanding how the output depends on the input. So you can just keep going with this. Here's lots of letters and subscripts and superscripts that tell you the same thing. So this is saying which layer you're in. This is our matrix. This is the row. This is the column. This is our vector of activations in this hidden layer. We take this matrix vector product, which looks like, this is the definition of a matrix vector product. And then we take our nonlinear activation, and that's how we get our next hidden layer. So this is the hidden layer k minus 1. This is hidden layer k. You keep going, you keep incrementing k to keep progressing through until you get to your output. Okay, so some common activation functions. There's the sigmoid, the one I told you about. Here is the sigmoid function. Here is its derivative, which will be useful for computing the gradients for W. And here are two others. This is just this one scaled in a different way, but it gets its own name. This one is pretty simple. It's called the rectified linear unit. If the input is positive, then then it does nothing to it, and if the input is negative, it replaces it with 0. So this is like the most trivial nonlinearity you could add, but even just that, it allows the neural networks to be very expressive. I might be jumping ahead here. There might be another slide on it, but if you had a linear activation function or no activation function, adding more layers wouldn't actually ever help. And the reason, it's hard. The only way I know of to explain it kind of involves some familiarity with linear algebra, but basically the idea is every matrix, when you take a vector and you multiply it by a matrix, it will stretch, squish, and rotate it in some way, and it could flip it in multiple different ways. And if you keep doing that over and over again, you're still ending up with something that's just stretching, squishing, rotating, flipping. And so you keep doing them back to back, and it would amount to just a single, there's a single matrix where multiplying by that matrix would accomplish the same thing. So if you're not having these nonlinear activations in the middle, adding more layers doesn't allow you to express any different sort of transformations. Yeah?
When would we use hyperbolic tangent or REL of U? Like, we've only seen the sigmoid tangent.
This whole field is alchemy. You try different ones and you see what works. You read what other people have done. You try those. I guess occasionally there will be something about your problem that'll suggest one or the other. But I have no answers to that question. The question was how you pick between these, if for those of you who didn't hear. Any other questions? Yeah. No, you could do whatever you like. Yeah, you could. I mean, different neurons in the same layer could have different activations. Yeah, this is just. Yeah, you can do anything. There's no rules. It's nice to have. I mean, you want things to be differentiable at the end, so that you can figure out what is the gradient of the log likelihood with respect to all of these different weights. This one is almost always differentiable. It's not differentiable right there, but I guess it ends up being fine. You're not there very often. Okay, yeah. No, it's fine. You don't apply the sigmoid to every element. It was a big expression, but there were pluses between. So you just, you're taking the dot product. I mean, let's see. Let's go back to this. So first you're taking, it's like a sum of a bunch of different things coming in, and then you pass it to that function. So it's not like you're applying the function to this and to that and to that. You do this, it turns into one number, you pass that one number through this function. That's right. Yeah, sigmoid gets applied to every h, and the h is a sum of a few different products that have come in. H is a scalar, yes. Well, okay. This h, I see what you're saying. Yes, this h is a scalar, this h is a scalar, this h is a scalar, h1, h2, h3, but we sometimes write this whole thing as a vector h. And then if we were talking about passing that whole thing through that way, then we'd be applying the sigmoid to each of these inputs. Okay. Cool. Okay. So we have the same basic idea as logistic regression. Going back to this equation, we are trying to find the weights that maximize the log likelihood. What is the likelihood? The likelihood is the probability, well, it's the product over all of our i's of the probability of the actual yi that we get from our data set, given the actual xi's from our data set, and given the vector of weights that we're considering using. So before, the w's were, all these matrices and some vectors, and now we're just kind of rearranging them into a single big long vector that we're trying to optimize. And so the log likelihood is the sum over the logs of these terms. So as I just said, this w, I mean, in this equation, it's convenient to just think of it as a single very long vector, but this is really many arrays of parameters, which you can then kind of reshape into a long vector if you want to think about it like that. Or not. You could just think of it as a set of arrays. And so then the dependence of P on W is much more elaborate in this neural network case than it was in logistic regression. But it's still the same basic form. And the last thing I'll tell you, just if you're kind of about this equation as applied to neural networks, is that if you're reading papers on neural networks, it's more common to use a theta than a W. You don't need to know that. It's just if you're going into this and you see thetas popping up, you can just know that that means what we've used the symbol W for. Okay, there is the attendance code for today. And any questions on this kind of basic form and how neural networks fit into it? Yeah?
Are we trying to maximize the probabilistic predictions from the neural network at the end?
Yes. We are trying to maximize the probabilistic predictions of the neural networks at the end. In particular, the probability that they assign to what they were supposed to predict. Okay. So, what I've showed you so far is kind of basically a per data point approach. So we think we have a given X, and we want to see what the neural network does with it. We want to see what output it comes up with. And so we take that single X, we run the computation forward, we get a single Y. We can, the way that, well, if we want to do it for another data point, also, that computation can be parallelized. And so we can write programs that, rather than doing them in sequence, do them all at once. And GPUs are very good at matrix multiplication. The hardware basically allows them to do lots of computations at once. And so if you can structure parallelizable computations as matrix multiplications, you can get huge speedups on hardware that is specialized for that. So that's the reason to try to think through, is there some nice matrixy way to write the computation of multiple different data points, well, the computation of the neural network with multiple different data points as input at the same time. So here we have one input. So this is our first data point. These are our three features of that data point. This is kind of, yeah, it's a three-dimensional data point, and we could compute a Y, a predicted probability coming out from in there. If these are sigmoids, then this will give us a probability. We can do the same thing for this other data point. Again, there's three features to it. And if we tried to do these at the same time, or if we tried to kind of write this computation in a simplified way, we'd end up with a nice matrix vector form. So here it is, if you just write it all out without any matrices. This is the form of Y1, this is the form of Y2, basically the same, but we're just changing some of these X11s to X12s, X21s to X22s, X31s to X32s, and then otherwise these are the same. Let's see, there is an example. That looks wrong. I'll have to look at this more closely and see if these details are actually correct. But that's the basic idea. Okay, so these are the computations we're trying to do, and now here's how we can write it in matrix form. So here each row is a data point. Each row is a data point in this hidden layer as well. Each column is a different neuron that we're thinking about. So this is the activation of the first neuron in the hidden layer when the second data point is fed in. That's what these numbers mean. And so this is the third neuron of the input layer, the activation that it takes on the first data point. This is the activation that the first input neuron takes when the second data, given the second data point. And so this sequence of hidden layer vectors can be computed as this matrix product. So if we want to look at the first row, second column, we go first row, second column, we take that dot product. That is in fact what we were looking for. I don't think I'll spend more time on this. I think you guys can look through and verify for yourself that the rules of matrix multiplication are making this computation do exactly what we want it to do. So that's nice. We can take a batch of data points, and now we have this matrix, and now we have this matrix. So we have batch number of rows, the dimension of the input layer, number of columns, and then we take this, we multiply it by this matrix, which will turn it into batch number of rows and n columns if we have n neurons in the hidden layer. And then we do the same thing. Basically, we're just, whenever we have something that is the activations of a layer, now we have batch different copies of it. And so we stack these together. We can classify multiple inputs at once. If we're running these computations on a GPU, it goes a lot faster. Yeah?
Why is the parameter called batch instead of like M or P or something?
The reason it is called batch is, let's say you have a million different data points. What you'd ideally kind of want to do is just run all a million of them through the network at once. But given the hardware we have today, it wouldn't fit in memory. And so you take a batch. You take like 2048 of your data points, and you run it through. And so this is like a batch of your million. And so that's why the number is called that. Yeah. Other questions? Okay. This is analogous to the same slide I showed you before, but now instead of these being ones, these can be other numbers, however many data points are in your batch. And it really does make things go a lot faster. I think this thing would be the difference between the biggest large language models today being feasible versus not being feasible. Okay, training neural networks. So here's how we do it. Here's how we steadily improve all these parameters. So for each input, for each data point, we predict the classification using the current weights. We compare those to the true y values using a loss function, and the loss function that I've talked about so far is the log loss, and that would be the negative log likelihood. So if we use the loss function, which is the negative log likelihood, we're trying to minimize the loss function, we're trying to maximize the log likelihood. We do gradient descent or gradient ascent, whatever you want to call it. So a higher value of the loss function is bad, lower value is good. You could use a 0-1 loss for misclassified inputs if you liked. The log loss is one we talked about. If you're just trying to predict a value, if you're trying to predict the rent of an office, like we were talking about in the linear regression lecture, then you might just say, what's the difference between the true value and the predicted value squared, because that's always going to be positive, and you want it to be small. And then you use gradient descent to minimize the loss, or you could call it gradient ascent to minimize the log likelihood if the loss function is the negative log likelihood. Okay, so if our neural network is outputting probabilities, then the log probability is going to take the following form. So if we're doing binary classification and we're outputting this probability, then let's say that the meaning of this output is how much probability it assigns to y equals 1. So before we were calling our two classes +1 and -1, and now we're going to be calling them 0 or 1. So yi, I think this equation obscures the fact that it's kind of like it's two options. It's like either yi is 0 or yi is 1, and it's going to take a different functional form. There's no in between for y. So if yi is 1, then it's this term. If yi, and this term is 0, so it cancels out. If yi is 0, then this term disappears, and we just have this term. So if yi is 1, we want pi to be as close to 1 as possible. All these numbers are going to be between 0 and 1. If yi is 0, we want this number to be as small as possible. And note, if yi is 1 and p is 0, that is, the model assigned 0 probability to what actually ended up being true, this gets penalized infinitely. So the log of 0 is negative infinity. And so we take the negative, the loss goes up to infinity. And likewise, if y is 0 and p is 1, same situation with the other term. So every data point will contribute some loss here, and then the total loss is what you get when you sum it all together. The yi's are given. This is the data set. This is what we're trying to predict. We don't have control over that. What we're trying to do is come up with the w's that make the p's be as good as possible for predicting the y's. Here is a picture of the log loss function when y equals 1. So when y equals 1, this term, you can cross it out. That's 0. We just have negative the log. It looks like this. So when y equals 1, very bad for p to take small values, good relatively for p to take large values. If we have this same log loss function, but now y equals 0, then it looks like this. We want p to take very small values, and it can be really, really bad if it is confidently saying that it should be 1 when it's actually 0. Yeah?
What is the range of the log loss function?
The range is 0 to infinity. Yep. Because these p's are going to be between 0 and 1, the probabilities, once we pass it through a sigmoid function at the end. Sigmoid function, the range of the sigmoid function is between 0 and 1, so we only need to consider the domain here between 0 and 1. And then the log is always negative, so the negative is positive. Okay, I think I'm going to skip this example of computing the log loss, but you can look at it later if you like. This is just plug in a certain value of y, a certain value of p, see what you get. Although, what I will say is, we run this computation for this data point, we run it for this data point, we run it for this data point, and then the last step is we add it all together to get the total loss. So we're adding up all the loss from all the individual data points to get the total loss for the whole data set. Yeah?
Does this log loss have any similarity to the log likelihood?
Yes, it is the negative. Yeah, it is the negative of the log likelihood. Yeah. Okay, optimization procedure. Now we're talking in terms of loss instead of log likelihood, but it really is just the negative of what we saw before. So it's gradient descent. This is a minus sign now. So this log loss is basically the negative of what we were looking at before. And the PI is computed by running through the network. We start with the x's, we compute all the values of the h's in the middle, and then we get to the end. Alpha is the learning rate. I promise I will show you a picture somewhere about what happens when it's too big. Where'd the picture go? Oh no, I can't, I'll find it somewhere on my computer if it's not here. Okay. So, the key thing that makes there would be a pretty basic and ultimately inefficient way of computing the gradient. It's just math. You have all your parameters. You compute the partial derivatives one by one. It would be annoying, but you could write code to do it. But there turns out to be a more efficient way to do it where you kind of run the computation in reverse. And the tool for that is the chain rule. I don't know if you guys remember from calculus, if you have some function that's a function of another function of a thing, the gradient takes this form. So f prime of x equals g prime of h of x times h prime of x. So all these derivatives, there are basic procedures to compute them. And we can use automatic differentiation software to do it. I use PyTorch. Other people in my lab use JAX, and they're telling me I need to switch to it. So maybe start off on that one if you're doing it. I've used TensorFlow before, and it's not very nice. The people who write these libraries make it pretty intuitive. You just define the computation, and then it can tell you about the gradient. And we're not going to really get into much of the details, but here's a pretty simplified example of what is called backpropagation, or just taking the chain rule back through the computation graph that you've defined. So the diagrams of neural networks that I was showing you is kind of a picture how this hidden layer depends on the hidden layer before plus the weight matrix in the middle. And so that's saying like how you move forward in the computation you get to the end. Here's another diagram of kind of moving forward with that computation. So here is a function of W1, W2, and W3. There is its form. And here is a drawing of the computation graph. So you do this, you pass it through the function to the fourth, you pass these two inputs through the multiplication function, and so on. And we can think of G as a composition of many functions and then use the chain rule to go back. And we can give these intermediate values names. So here, let's say we're starting with these values. And then we raise it to the fourth. We'll call this intermediate value A, and it takes that value. We'll call this intermediate value B, which takes that value, so on for C, and so on for our output G. And then we can say that G equals B plus C, and we can compute the partial derivatives of G with respect to that. And this is straightforward. This is a simple operation. We always know what this is going to be. This is a property of the plus operation. It doesn't matter what the inputs are. And then B is defined in terms of A times W2. So now we can write the partial derivative of G with respect to A in this form. So we have the partial of G with respect to B times the partial of B with respect to A. Well, this we got from this property of the plus operation, and this we get from the property of the times operation and the this value. So this is so we're kind of looking at local information in the computation to go backwards with ever more distant relations between variables. I mean, G and A are more distant in the computation graph, but we can come up with this relation between them, this partial derivative. Likewise for the partial of G with respect to W2, and then we can go back even further. We can calculate this partial derivative on the basis of what this local operation is doing. And we're chaining these together. We're multiplying these partial derivatives, and that gives us the partial derivatives at the end. So now, look, we've got the partial derivative with respect to that, and with respect to that, which is what we were aiming for. And in this case, you could have just redone your work every time. But in a computation graph that's more elaborate, it's really helpful to have this DGDB cached, because you'll end up using it for everything that precedes it in the computation graph. So you basically cache the gradients of all of the output with respect to a hidden layer value, and you use that for computing all the other gradients. Okay, here is a picture of kind of how this would work in PyTorch, which I just wrote like yesterday or the day before. So here you create some x and y, you give them values, you say you're going to need the gradient later, you compute any old function, and then you call z dot backwards, and then it will tell you what is the gradient of z with respect to x, what is the gradient of z with respect to y. And I've printed that out for you. Very simple equation. You could have done this yourself, but if it gets, if this expression was much more complicated, maybe over hundreds of lines of code, okay, tens of lines of code usually, this will help you a lot, especially if those tens of lines of codes have like for loops in there. Here's a more elaborate example, where this is a vector x, a vector y, a matrix M. We're going to want the gradient with respect to every single one of these locations in each of these tensors. It can even do things like you invert this matrix, and now this means matrix multiplication. So you're doing this matrix vector product, this vector vector product, and now that's our new z. And now we take the gradient of z with respect to all three of these different things. Those are going to be the same shape as what we've got. So this is a 4-dimensional vector, so the gradient's a 4-dimensional vector. This is a 4x4 matrix, so the gradient's a 4x4 matrix. So that means if I increase this by a millionth, z is going to go up by that times a millionth, which, I don't want to calculate that. So that's what PyTorch and other libraries can do for you. Yes? Z dot backwards says, okay, so here I'm warning it. I'm going to want gradients where this is in the denominator, and this is saying, okay, here's what's in the numerator. So this is telling me I'm going to want to compute a few things at once. The gradient of z with respect to x, with respect to y, and with respect to m. And so then in this step, it'll compute basically all of these things, and this will be dz dx, dz dy, and dz dm. You might need to run separate lines of code if you want different things in numerators, but it's one line of code if you want the same thing in the numerator and different things in the denominator. Okay. Yeah, I think we can cover this. Oh yeah. I'm just going to skip ahead to this, and I think we'll cover the stochastic gradient descent in the next lecture. So what happens if you have too high a learning rate? So here we're kind of moving around in two-dimensional space. That's down here. This third dimension is just depicting what the log likelihood is. So in this case, we're doing gradient ascent. We're trying to maximize it. If we're here, we get this value. If we're here, we get that value. So we want a value that's kind of hiding behind there. That'll be the maximum. So what happens if we start right here? Okay, the gradient is pointing to the left. That would be the direction of steepest ascent, the direction we want to go. If we have a small alpha, then we might move a tiny bit there. What happens if we have a really big alpha? If we have a really big alpha, then we might move quite far in that direction. And now you'll notice we've gotten farther away from our target because we've overshot it. Now what happens if we do it again? Now with this loss function, as you get further away, it gets steeper and steeper. And because it gets steeper and steeper, the gradient magnitude is bigger. And so the next step will be even bigger than that one. So it'll go back the other way. Okay, well, it's good to go back the other way, but it's bad to go so far back the other way. And now you can look here, it was a little bit steep. Here, it's even steeper. And so when we go back with the same learning rate, we'll overshoot it even worse. That's bad. One of my colleagues, I saw this poster on his wall when I was doing a Zoom chat with him. If it's not working, keep calm and lower your learning rate. Maybe most of the time it'll go slower, but occasionally it'll go from not working to working. Okay, I will see you guys on Thursday.